Now we'll be going over deformations in a system of actually loaded bars. So many structures consist of more than one actually loaded member, and for these structures, axial deformations and stresses for a system of pin-connected bars must be determined. So we approach this problem through a study of the geometry of the deformed system by means of a deformation diagram, and then from which the actual deformations of the various bars in the system will be obtained. So in analyzing these structures, we begin with a free body diagram showing all forces acting on the key elements of the structure. Then investigate how the structure as a whole deflects in response to the deformations that occur in the axial members. Okay, and what do we mean by this? Well, we will go over this in example M5.3. So we have an assembly that consists of a rigid bar ABC. Okay, so this rigid bar will not bend or deflect. Okay, two fiber reinforced plastic rods or FRP rods 1 and 3. You can treat them as steel rods or whatnot, but they are rods, so they will deform, and they have they are supported by the rigid bar is also supported by a FRP post. Okay, at 2 here. So since this is an FRP post, that means that this will also deform. All right, and this is where our deformation diagram comes in. So the modulus of elasticity for the FRP is 18 GPa, and we are supposed to determine the vertical deflection of joint D relative to its initial position after a 30 kilonewton load is applied. Okay, so a 30 kilonewton load is applied here. That means that this will elongate right here. This when this will elongate, or when this a force is applied here, it will rotate about B. So this will be stretched also. So this will elongate as well. While this is supporting the rigid bar here, this post is supporting the rigid bar here, and therefore this will be under compression, right? So since this is under compression, this will deflect downwards. Okay, and that is why we cannot determine the deflection of joint D here by simply equating it to the deformation in joint D. Okay, because this will change, and because this will change as well. So we will start by analyzing the forces in each of the bar by conducting equilibrium equations, and then we will determine the deformation in each segment, and then apply those deformations in the deformation diagram, and then after that we can determine the deflection of joint D. So applying the drawing out the free body diagram, we have F sub 1, F sub 2, and F sub 3 if you apply method of sections here. All right, at this point we have this free body diagram for the rigid bar. We know that F sub 3 is just equal to 30. All right, so if we take moment at B equals 0 and take counterclockwise moments as positive, okay, this is clockwise. F sub 3 negative times 1.8 plus F sub 1, right, times 2.4. This is counterclockwise, so that's positive, is equal to 0. And we know that F sub 3 is equal to 30, and so we know that the force in force 1 or segment 1 is equal to 22.5 kilonewtons. Now summing up forces along the y-axis, since we know F sub 3 and F sub 2, we should also be able to get F sub 3 and F sub 1 rather, we should also be able to get F sub 2 by summing up forces along the y-axis and equating to 0. So F1 plus F2 plus F3 is equal to 0. And therefore, F2 will be equal to negative 52.5, indicating that this is compression. Okay? So, judging by this, we will determine the axial deformation in each of the three members, and we will see that applying equation M5-1, we have For member 1, 9 mm elongation. Member 2, negative 7 mm or 7 mm compression. And for member 3, 10 mm elongation. So where does this fit in our system, right? In our statically indeterminate system, or in our system of actually loaded bars. Rather, this is not statically indeterminate yet. Okay, so this is where the deformation diagram comes in. So what is a deformation diagram? It is drawn to define the relationships between the rigid bar deflections at A, B, and C, so the member deformations can be related to rigid bar deflections. Okay, so since this is supposed to elongate, it will go up here. This is supposed to compress, so it will go down here, and then this is supposed to elongate, right? This will go down here as well. Okay, so what do we notice? We notice that here VB right here and VA is most likely just equal to the deformation in segment 1 here for VA and the deformation in segment 2 for VB. However, VC is not equal to the deformation in segment D, as they are as this is dependent on the geometry of this setup right here. So we find that we form similar triangles, namely this triangle, and this triangle right here. Okay, so how do we do that? Well, what we can do is that we can pass just to, because if we use these triangles right here off the bat, we don't know the distance from this point to this point, or from this point to the intersection of this line and this line. If we pass a line here, okay, and extend the triangle downwards, right? So we have this triangle right here and this triangle right here, and we know this length and this length already, so this is easier for us to carry out. All right, so by similar triangles, that is VA plus VB over 2.4 is equal to VC over 1.8, and that is what VC minus VB, rather, because this is VC and this is VB. Okay, from the let me draw that out. Okay, from this deformation diagram, it's this length right here, so that's VC minus VB. Okay, so since VA is just equal to the deformation in segment 1, and VB is the deformation in segment 2, we can easily determine VC, right? Okay, so next, the deflection of joint C can be computed from the sum of the rigid bar deflection at C and the elongation in member 3. So that is 29 mm. That's 19 plus 10. And why is that so? Well, the deformation in the rod, if you see here in this segment, or in this deformation diagram, the deformation in the rod is local here. Okay, it does not affect rather this deformation here, or this displacement here, and that is why we are just adding this deflection to the elongation in the segment 3. Okay, and therefore we have 29 mm.